Yay, I think it's all working. Okay, folks, let's get this show on the road. So you can hear me okay, right? I'm assuming it's okay. Let me know if there's any problem. Speak up. Okay, so today the topic that we're going to discuss is the variational principle. So this is a new topic. It's a new approximation method. And I would say that it's not as important as perturbation theory. It's not used as widely as perturbation theory, but it is still very, very important, and it's used a lot. So it's really useful to learn. It's very powerful. More powerful than you would expect once you learn it. And so so what is it? Let's talk about it. So let's discuss the main idea of the variational principle is that suppose you have some system that is described by some Hamiltonian H. Then what happens is that if you consider any possible wave function that you might come up with, any arbitrary state, any arbitrary function, then it turns out that the expectation value of that state, the expectation value of the Hamiltonian for that state, which is equal to this thing that you know, this integral, then this expectation value, which I can write as an integral, let's write it out, psi star of r, h psi of r, d cubed r for 3 dimensions. This integral is greater or equal than the ground state energy of the system. This is the true ground state energy. That's it. That is the whole thing. It's so simple to write out. That is the whole thing. And so you look at that and you think, well, how can that possibly be important? And yet it is extremely important. And the reason it's important, first I'll tell you why it's important, and then we'll prove it, and then we'll use it in some examples so you can see for yourself. But why it's important is because what happens now is that you can assume this is how you use it. To use this, what you do is you assume that the wave function, that the ground state wave function is equal to some function, some arbitrary function of x parameterized by some other function, lambda, some arbitrary parameter. Then what you do is you calculate the expectation value of the Hamiltonian for that state, which is a function now of this parameter. Then what you do is you know that this thing that you calculate is going to be bigger than the ground state energy. So what you do then is you minimize this with respect to lambda. Then you find the parameter lambda that gives you the minimum value, and then you plug in that lambda to find the ground state energy and the ground state wave function. Okay, so that's what you do. That's how you use it, and this is very powerful and very important. For example, this is how people solve the problem of superconductivity in metal. Like, for example, when you get some metals like lead, you cool it down, it has zero resistance, it's a superconductor. I have mentioned this to you before, and that was a very difficult problem to solve. It took 50 years to solve. Einstein tried to solve it and failed. Feynman tried to solve it and failed. It wasn't until Bardeen, Cooper, and Schriever solved it in 1957, and the way they solved it was by using the variational method. They assumed a certain ground state for the electrons in a superconductor, and they minimized it. they calculated the expectation value of the Hamiltonian, and they minimized it with respect to some parameters, and they plugged it in, and they got the wave function for the superconducting ground state, and they got a Nobel Prize. And now we remember them and use it all the time. So it's very important. Okay, so now but to understand it, you got to use it, you know. So let's do that. So first, let's prove it. Let's prove it, and then we'll use it, and then you'll really see. It's actually pretty simple to use. All this stuff is fairly straightforward. Okay, so let's prove it. So so let's consider a system that's described by some Hamiltonian, okay? And then let's assume that we, then we know that there must be some eigenstates that exist. We know that there must, so we know that there must exist some eigenstates. We don't even need to know what they are, but we just know they exist. Must exist, the eigenstates must exist such that H acting on these eigenstates is equal to the energy of each eigenstate. We don't even need to know what that energy is, but we just know it exists. There's got to be some, you know, you can always diagonalize a Hamiltonian. It's a Hermitian operator. So we know that these states must exist. And so now what we do is let's consider an arbitrary function, an arbitrary state, psi of x. So I'm going to do this in 1D. Let's do it in 1D, 1D, and the generalization to 3 dimensions is simple for this one. So let's not worry about starting with multiple dimensions. Let's just do it all in 1 dimension. So let's consider an arbitrary state, psi of x, and let's assume that it's normalized. Then the trick is that we know that we can write psi of x as an expansion of the eigenstates of the Hamiltonian. And we can always do that because the eigenstates of a Hermitian operator form a complete orthonormal basis. So we know we can do that. So let's do it. So let's write it out as an expansion of those eigenstates. And we don't even need to know what they are for this proof, but we just need to know that they exist. And so then what we can do then is now let's calculate the expectation value of the Hamiltonian for that state, psi. And this is equal to, right, psi of x, h, psi of x. Let's calculate this. And so then what we see is the expectation value of the Hamiltonian for this state, this arbitrary state. And remember, this state is not necessarily an eigenstate, it's an arbitrary state. Then this, this expectation value is an integral. So let's plug it in. It's just going to be an integral over x. And it's going to be, I'm going to have psi star of x. and psi star of x will be the sum over n Cn star phi n star of x, and then h, and then I have to plug in here psi of x. But now I'm going to plug in the expansion. But you know the trick, the math trick, when you have multiple expansions, you got to give them, in an integral, you got to give them different indices. You guys know that trick. So then I got to give that guy n prime. So this is C n prime by n prime of x. Okay, so that's it. And so now let's just crank through it. Because now what we do is we know that this then is equal to, so now let's just rearrange stuff. So I can pull the sum out. And so I have a sum over n and n prime. And then I can pull these coefficients out. They're just constants. C star, the complex conjugate of C sub n times C sub n prime. And now I have this integral, though, is phi of n star of x h phi n of x, where that's n prime, dx. Okay, and so now what happens when h hits phi n prime? Tell me, somebody.
E of n.
I'm sorry, let's see, I gotta turn my volume up a little.
Is that E of n, E sub n?
But it's hitting phi of n prime.
Oh, E sub n prime.
Yeah, perfect. That's exactly right. And so we see then that the expectation then of the expectation value of the Hamiltonian is equal to, now we have this sum n prime c n star c n prime, and I can bring that, now I can bring that energy out, E n prime, and now I have this, the integral over x of phi of n star of x phi of n prime of x. Okay, and then so what does this thing equal? Well, somebody tell me.
To Kronecker delta?
Exactly. Because these are orthonormal functions. See, I don't even know what function, I don't even need to know them. I just know that they're orthonormal because of the eigenstates of the Hamiltonian. So that's delta n prime. And so this thing then becomes the sum over n prime c star n c n prime delta n prime e n prime. And so what this does, you guys know the trick, this collapses the sum. It collapses the sum, and then we have n prime goes to n. Okay, so that's what always happens when you have a Kronecker delta in there. And so now we have h psi is equal to, now it's the sum over n of c star n cn, which is cn squared e n. Okay, you guys see that? Let me make sure I did the algebra right. Yeah. Okay, so that is the expectation value of the Hamiltonian for this arbitrary function. So it's kind of cool. It's a cute little mathematical thingy. But now let's do a trick. Now comes a big trick. We're going to say, suppose that we have, suppose we were to replace the, suppose we were to do this trick. Look at this. Suppose I was to replace En with the ground state energy, the true ground state energy. What then is the relationship between this object and this object? How are they related? The object, what is the relationship? So this is object 1 and this is object 2. What is the relationship between 1 and 2? Somebody tell me. Are they equal? Yes or no?
Isn't it 2 is always less than 1 or equal?
That's exactly right. Because we know that the ground state energy is always less than or equal to E sub n. And so therefore, I have 1 is always greater than or equal to 2. So what I can do then is I can replace this, and I can say that this object is always greater than or equal to that object. And so that means that now I have that H, the expectation value of the Hamiltonian is greater than or equal to this thing, number 2, and I can bring the ground state energy in front, E ground state, and this is a sum then over C sub n squared. Okay? But what then is this sum over C sub n squared? Can somebody tell me what that is?
It's 1.
Right. It's equal to 1 because of the normalization of psi, because I started with the normalized psi. And that's something that you guys derived last semester. And so that then gives us that the expectation value of H is greater than or equal to the ground state energy. Boom. QED, whatever the hell QED means. It's just something you write at the end of a proof. Okay, and in case you can't remember this last step, I mean, I'll just remind you, like, if I have this last little step, if you have 1 is equal to, if you have a normalized function, I'll just remind you, a normalized function means that psi star of x, psi of x dx is equal to 1. But then if I plug in those functions, and I know that 1 is equal to integral of Cn star, Cn prime. I'm skipping a few steps, but I'm just kind of, just want to write this in for you guys. Phi n of x, phi n prime of x dx. This becomes delta n prime, and so we have 1. Oops, screwed up here. Forgot to do the little sign n prime. So that becomes okay, so that's just a little lightning proof of that 1. So you guys can look at that. Okay, so we've proved it. And so that's it. So that means so that's kind of an interesting thing. So that means that this quantity psi of x, the expectation value of the Hamiltonian for any state, any function, is always going to be greater than or equal to the ground state energy. And so it's an upper bound. It always provides an upper bound. So that's kind of interesting. So, okay, so now let's actually use this to do something useful. Okay, so now let's use it. And what we're going to do is we're going to ask ourselves a question. So suppose somebody says, hey, guess what? I figured out how to make a really tiny simple harmonic oscillator. I got a mass, I got a spring K, and it's a tiny harmonic oscillator, and it's really teeny tiny. And so it's so tiny that quantum mechanical effects become important. And so what I want to know what I want to know is, what's the ground state energy of my tiny harmonic oscillator? And so this is a tiny simple harmonic oscillator. Now, you already know the answer because you spent a lot of time last semester studying the simple harmonic oscillator, but I want you to remember that it's not an easy problem, to solve. I mean, there's 2 ways to solve it, and I'm assuming you guys did it both ways. You can do the differential equation, solve the differential equation, or you can do the clever ladder operator algebra. But both of those are not completely, trivial things to do. So it's a hard problem, actually, because, if you want to find the ground state energy, then you have to write out the Hamiltonian. It's equal to p² over 2m plus the kinetic energy, 1/2 kx squared. And so another way to write it is we like to write it like this. The kinetic energy is negative h by square root over 2m, second derivative with respect to x. Let's just do this in 1D plus 1/2 m omega squared x squared, where omega is equal to the square root of k over m. Your old friend, the spring frequency. You guys all know that. Okay, and so then to find the ground state energy, what you have to do, which is what you did last semester, you have to solve this equation. H psi sub n equals En psi sub n, the Schrodinger equation. You must solve. And it's really hard. You know, it's like, it's a hard problem because it's a hard differential equation. But you did it last semester. And you remember, if you just grind through the differential equation, it's actually quite complicated. There are all these special functions. I don't know if you guys did it that way, but you know, I remember it's a really hard problem. Okay, so what we're going to do is we're going to skip all the hardness, and we're going to pretend that we don't know. Suppose no one ever showed you how to solve it, then you probably wouldn't be able to solve it on your own unless you're some kind of math genius. So let's suppose that no one ever showed you how to solve it, and so you want to solve it. So what you do is you say, okay, well, this is how it works. You draw the potential. I mean, this is what people actually do out in the real world, because you're often presented with weird Hamiltonians. And so what you do is you draw the potential, and you say, okay, that's a parabolic potential. Okay, it's a parabola. V of x as a function of x. It's a parabola, right? 1/2 kx squared. Now, we know the actual solution, right? You guys remember the solution. It's this function. What do I call this function? You guys know, what's that called? What's the ground state of a simple harmonic oscillator? Somebody tell me.
Isn't it like a Hermite polynomial? How do we say it?
I think it is Hermite polynomial. Yeah, it might be, but I'm talking about the ground state. There's an even simpler name for it than that.
Is that a Gaussian?
Yeah, it's a Gaussian. It's just something to remember. You know, the true ground state of a simple harmonic oscillator is a Gaussian function when you go through all the math. E to the negative alpha x squared. That's a Gaussian. Oh, okay. So, but suppose you didn't know that. Then what you know then, this is what you know, is that the ground state, it's like, this is how you do it. You think it, you use reasoning. You go like this. You say, okay, that's my potential. Oh, that's a pretty crappy parabola. You know, you say, this is what you do. You say, okay, I got some potential. Now I know there's a ground state energy. I don't know what it is, but I know there is one. And I know that if I'm at this ground state energy, then when I'm in this region of the potential, the classically allowed region, then I get a big antinode for the ground state. You know, I get this, up, right? An antinode, because you know, always get for the ground state, you always get one big blob. You guys know that from, you know, particle in a box, right? Particle in a box, the ground state looks blob like that. So, and then you know that in this region, the classically forbidden region, you know that it's going to be some kind of dying exponential type thing, right? You know that. So without doing any math, just simple physical reasoning, you know that that's what the ground state wave function is going to look like. But to actually solve for the function, and we know the answer, it's a Gaussian, but to figure out, to actually solve that it's a Gaussian, it's really hard. In fact, it's probably beyond the mathematical capabilities of any of you, probably, except for maybe there's one or two math geniuses among you. I know that when I was an undergrad, there's no way in hell I could ever actually solve this problem on my own without someone showing me all the tricks. So it's a really hard problem. But now we just, but even without doing any of the fancy math, any one of us, any one of you could figure this out, that you know that that's got to be the shape of the wave function. So then what you do is you say, okay, well, I don't know the true functional form, so let's just guess a form. So let's guess a function. And the function that we're going to do is we're going to say, okay, so this is my potential. So what if my functional form, it looks like this? Let's just guess it. Let's just say it goes blop, blop. That's going to be my wave function. That's my guess. Is that, and I'm going to assume that it goes to some that has it has some shape, and that here it's 0. So you see what I'm saying? And so I'm going to assume that my wave function psi of x, my ground state, my assumed ground state, is equal to this function. And what that function is, it's an upside down parabola. A squared minus x squared. That's it. Oh yeah, but then I'm going to square it. So it's like to the 4th power. So I'm just going to assume this function. And I just made this up. And the point is it would work no matter what you do. I'm just going to assume that. So you see it's like an upside down parabola, although it's a parabola squared, but that doesn't really matter. And if you work the numbers, you can see that it crosses 0 here at x equals a. And at the top here, when x is 0, it's equal to a to the 4th. You see that? And so that's my function. And so you might ask, well, how did I get that function? And the answer is, I just made it up. I could have chosen any goddamn function that just sort of looks like that. And I made it up, and it has an arbitrary parameter here. Arbitrary parameter. And so look what I'm going to do. What I'm going to do is I'm going to calculate. I'm going to use the variational principle, and I'm going to calculate the expectation value of the Hamiltonian for this wave function. All right. And then I'm going to calculate it. Psi of x, h, psi of x. And I'm going to grind through it and calculate it. And then what am I going to do with the answer? Can you guess? If I calculate it, then it's going to be a function of what variable? Suppose I calculate this integral for this problem. It's going to be a function of what variable? Tell me.
Is it A?
Yes. And when I calculate this, and I'm going to get this function of a, whatever the heck it is, I know that this function is greater than or equal to what?
The ground state of what we want.
Yes. The true ground state energy. I don't even know what the ground state energy is, but all I know is that whatever it is, this function of a is bigger than that. And that's actually a very profound statement, because what that means is that for this function of a, if I plug in any value of a, the number I get is always greater than the ground state energy or equal to it for every a. So what that means then is that to get the best estimate of the ground state energy, what am I going to do with this function? What am I going to do with it? Tell me.
Minimize it?
Yes. How do I minimize it?
Do the differentiation with respect to a.
Exactly. And once I get that derivative, what I do with that derivative?
Find the derivative which equals to 0.
Exactly. And then what I do is I find the minimum value, I'll call it a min, by solving this equation, and then I plug it in. And that gives me then my best estimate of the ground state function, psi of x a min, and the best estimate of the ground state energy is going to be equal to that expectation value of the Hamiltonian for psi of a min. Do you see what I'm saying? That's how we use the variational principle. That's how you do it. So let's do it, because it's it's one thing to talk about. Now let's actually do it. So let's calculate it. And so here we go. So let's calculate the expectation value. So it's going to be, first I do this guy, it's going to be a squared minus x squared squared, and that's going to be psi star of x. It's a real function, so I don't need to worry about this complex conjugate stuff. Then I'm going to put in the Hamiltonian, and the Hamiltonian is minus h bar squared over 2m d squared dx squared plus 1/2 m omega squared x squared. And then I got to plug the wave function again, that's the Hamiltonian. And then the wave function again is a squared minus x squared squared. And this is it's an integral, and it's an integral over x. And what are the limits of the integral? What are the limits of the integral? What are the limits?
-a to a.
Yes, exactly. Because remember, my function is 0 here. That's my function. You see, this is the function I chose. Just some weird little arbitrary function I just made up. It could have been anything, really, you know. And so that's exactly right. So it goes from -a to a. And so now I got to calculate this. Now, then I got to calculate this and then minimize it, right? That's the trick. Not because it's now a function of a. Okay, but actually, I'm missing something. And this is just a little nuance of the variational principle. I am missing something. What am I missing? Now go back to the derivation of this whole scheme. What am I missing?
Normalization constant?
That's right. That's right. Because remember when we derived this variational principle trick, the wave function had to be normalized. That was part of the proof. Remember, we did that. And whereas this thing, when I give you this function, I just made this function up. You know, it's not normalized. Because when you just make up a function, it's usually not normalized. You know, it's just made it up. So what we got to do then is we got to normalize it. And so this is how you ensure normalization. You ensure normalization by dividing it by the integral of something times something. What are those things? What do I divide it by?
Psi star and psi.
Exactly. A squared minus x squared squared times a squared minus x squared squared. Psi star of x times psi of x. This is to ensure normalization. And if that does not make sense to you, then go think about it for a while, and you'll see that this is, in fact, will ensure normalization. Okay, so that's my expectation value. That is the expectation value for the normalized wave function. Okay, so now you see I have basically now I have three integrals that I have to solve. 3 integrals. You can see that I got to do this integral, the normalization integral, right? And then I got to do the kinetic energy integral, right? And then I got to do the potential energy integral. Okay, you see it, how there's 3 integrals in this mess, this big mess of stuff. So let's do those 3 integrals one at a time. Let's just grind through it. So let's do the first integral, which is the normalization integral, and that's going to be -a to a of this can be psi star psi dx is going to be x squared minus a squared 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 to the 4th power dx. And so if you grind through that integral, then if that actually is not, I think it's not like a completely trivial integral. But if you grind through it, then you're going to find that it's equal to 256 times a to the 9th divided by 9 times 7 times 5. After you just do some, I don't know, some integrate by parts, or I don't know, you just do some tedious integrals, and that's what you're going to get. Let's not worry about that detail. So now let's do the second integral, which is the, let's do the potential energy integral. Negative a to a psi star potential energy psi dx, which is equal to negative a to a times 1/2 m omega squared times psi stars x squared times, I'm skipping a little bit of algebra, x squared minus a squared to the 4th power dx. Okay, and you can see that that's what you'll get. I hope you can see that without too much trouble. And then if you grind, so that's a tedious integral, but it's not that hard, but it's a lot of tedious, you know, algebra, or you could plug it into Mathematica or whatever. And you can see you get 1/2 m omega squared times 256 times a to the 11th all over 11 times 9 times 7 times 5. I don't think I've ever actually solved this integral. I don't know how they get those weird numbers. I just copied this out of a book, but it's still kind of, you know, kind of cute and funny. Okay, now let's do the last one, 3. And now this is going to be the kinetic energy integral, psi star of x bumping up against the kinetic energy, which is operating on psi of x. And so that's going to be this negative a to a. It's going to be a squared minus x squared times negative h bar squared over 2m, second derivative, acting on a squared minus x squared dx. All right, well, this one is a little harder. It's a lot of more tedious bullshit that you guys have to do. You know, it's tedious, but it's not hard. Like you could do it. You know, it's not like some insane differential equation that you have no idea how to solve. It's just a stupid integral of a stupid polynomial. You know how to do it, and some dumb derivatives. It's tedious, but it's doable. So let's say that you did it, and you get negative 256 times a to the 7 over 7 times 5 times 3 times negative h bar squared over 2m. Okay, that's what you would get if you grinded through all that algebra. So now I got these 3 pieces. Oops, didn't do that circle correctly. Now I got these 3 pieces, and so now let's just add them up. And so then I see then, I add the 2 and divide by the 3rd, right? You know, I just add them up and divide correctly. And then what I get is that the expectation value of the Hamiltonian, once I do that algebra, which is a function of a, is equal to 3/2 h bar squared over m a squared plus 1 over 22 m omega squared a squared. Okay, and so I know that this is going to be greater or equal to the true ground state for any a. So what do I do to this thing now? What do I do to this function? Somebody tell me. What do I do?
Take the derivative with respect to a.
Exactly. That's exactly right. But I'm going to be tricky because some smarter person than me actually solved this problem and wrote it and stuck into a book. And what the smart person noticed is that to make the problem a little easier, we can just do the derivative. We can minimize with respect to a squared. And it's the same thing. You know, if I minimize it with respect to a squared, it's also going to give me the same answer because of the nature of that function. So just a little mathematical convenience. So I'm going to take the derivative with respect to a squared. And when you do that, this is what you get. You get negative 3/2 h bar squared over m a to the fourth plus 1 over 22 m omega squared. And now I set it equal to 0. And when I do that, I solve that equation and I find that a squared is equal to square root of 33 times h bar over m omega. Okay, and so now what I can do is, I got it, so that's my minimum. I'll call that a squared minimum. That's the minimum. And so so now that I have the minimum, to get my ground state energy, I say that the ground state is going to be, I say it's approximately equal to, well, how do I get, so what is the ground state energy? How do I get it? What do I do?
Plug in that a minimum into the function.
That's exactly right. This is the assumption. Exactly, that's the assumption of the variational principle. I assume that the ground state energy is approximately equal to that expectation value of the Hamiltonian using the minimum, using the function that minimizes that number, that function. Okay, it's harder to say than to do. So let's just plug it in there. And so you plug it in, and then let's skip some algebra. And what I get after you do the algebra is this: 1/2 h bar omega times square root of 12 over 11. Okay, that's the answer I get. And what's the true ground state energy? Somebody tell me, what's the true ground state energy? What is the true ground state energy of the simple harmonic oscillator? Somebody tell me.
1/2 h bar omega.
That's right. And so notice how the answer we got is bigger than that, okay? It's bigger because it's an upper bound. And so, and notice that we're only 5% off. So that's pretty good. That's pretty good. So I just want you to see the power of this technique. You see that? It's like I looked at the potential, you know, going back to my guess here, I'm putting a box around it. You know, I just came up with this stupid function, which is, you know, and it could have been anything, you know, I could have just done a triangle, you know, I could have done any function. And you can see I got a pretty good estimate of the ground state energy. So that's pretty cool. I want you to see the power of that, all right? Okay, so now let's actually use it to solve.
I got a question about that.
Yeah.
When we're choosing our wave function, if we choose it so that it matches the real wave function more closely, could we expect our expectation value of the Hamiltonian to be closer to the real ground state energy?
Of course. I mean, sure.
So,
you can imagine how it, you know, there's a limiting function to the true energy. Yeah.
right, so if we were to use a triangle like you suggested, we could expect that our expectation value of the Hamiltonian is probably going to be further off, right? The worse a match we have, the further away you're going to be.
Yeah.
Okay.
Absolutely. Okay.
One
Yeah.
more question. Could you use this method to solve like any differential equation? Is this kind of like if you're able to graph it, kind of, you can just guess it. Is this kind of?
I don't know about, I mean, well, I guess, yeah. I mean, you could, but what we're solving for is the ground state energy. So, I mean, you could do this for any operator, you know. So you could say, you could define any operator and you could say this operator has an orthonormal set of eigenfunctions and eigenvalues, and we want to know what is the lowest eigenvalue. And so, yeah, this is a completely generalized technique. You see that, but the only trick is that that operator has to be a Hermitian operator, so that you know that it has an orthonormal basis of with real eigenvalues. So yeah, it's totally general. I mean, the proof that we did was completely general. Okay, so now let's use it to solve a hard problem. Let's do a really hard problem. Let's now solve an important and difficult quantum mechanics problem. A genuinely hard problem. And this genuinely hard problem is, let's find the ground state energy of helium, a helium atom. And so here's helium. This is +2 in the nucleus, and I have 2 electrons going around it, right? So there are 2 electrons going around a nucleus that has Z = 2. That's helium. And let's find the ground state energy of helium. Now this is the so this is how it works, like in quantum mechanics. Like, I'm an experimentalist, and so I always view things from the perspective of an experimentalist. So let's assume that there's some experimentalist 100 years ago, and that experimentalist takes some helium, and then that experimentalist can make an electron gun, because that's not hard. An electron gun is an easy thing to make. You just get a hot filament. I've made electron guns before. It's easy. You just get a battery and a wire, and you make it really hot by passing current through it. And then what you do is you have a plate here with a hole in it, and you ground this guy, and then you put another plate here with a hole in it, and you put here a battery here, make this plus minus with a voltage, and then electrons are going to jump off the hot filament, and they're going to go through this hole and be accelerated out here with an energy equals to EV. Okay, so I just want to give you a sense that it's easy to make an electron gun. So that's an electron gun. And suppose I make my electron gun, and then I have my glass tube of helium, or let's say it's not a glass tube. I don't know. It's just I got some helium here, and then I notice that I ionize it. So let's say I have some way of detecting the ionized helium. Like I could have some other electric field that accelerates the ionized helium. Neutral helium is not ionized, is not accelerated, but ionized helium is. So let's say that I can detect. I have some way of detecting the ionized helium. Ionized helium, and so I do this, and this is a power supply here. And then I ramp this voltage, because that's just a power supply. I just turn the knob. They even could do that 100 years ago. And I notice that ionization, complete ionization, meaning both electrons are knocked out, complete ionization happens when the energy of my electrons I'm shooting at it is equal to, what's the number? 79 electron volts. Okay. So I just noticed that I don't get doubly ionized helium until I crank my voltage up to 79 volts. And then I noticed that suddenly some of the helium, I start producing doubly ionized helium. So that's a real experiment. You could really do that. Doubly ionized. And so let's say that you do that experiment. And so now what you have just discovered is that the ground state energy of helium is equal to what? Somebody tell me. Tell me. You are an ancient physicist from 100 years ago, and you have just discovered that the ground state energy of helium is what? What number?
79 EVs.
Well, is it plus or minus?
Minus?
Right, because it's a bound state energy. Those 2 electrons are trapped by 79 electron volts. You liberated them by giving them plus 79. You took them out. I just want you to to see that they used to be down there, and you kicked them out with some positive energy. Okay, so that means that your ground state energy is negative 79 EV. Okay, we just discovered the ground state energy of helium. Okay, 79. Okay, well, what the heck? So now you want to write a paper. You're so excited that you want to write your paper in a nice journal, but to get your paper accepted into a high impact journal, you have to do some theory. You have to explain your experimental result. And this is true. I mean, I publish papers all the time, and so I'm always doing this. You know, I'm an experimentalist. We take data and then we try to explain it, because I know that I cannot get my paper published in a high impact journal unless I can explain the data, or at least come up with a nice story, you know, that partially explains it at least. Okay, so we got to explain it. How? How do we explain it? Okay, so you're sitting there thinking, okay, how the hell do I explain this? And so suppose that you did, you know, quantum mechanics has just been invented, and so you go, oh, there's this new theory, quantum mechanics. Let's try to explain it. So I know with this new theory of quantum mechanics that, you know, I have this nucleus of plus 2e, and my helium has 2 electrons. And I know that, you know, I'll call this one electron 1, and I'll call this one electron 2. and I know that there's some distance between these electrons, and I'll call this distance R1 minus R2. So, you know, you know this to be true, because you sort of know, okay, you know, this is the geometry of helium. And then you say, okay, now I'm going to use this newfangled quantum mechanics to explain this. So you go, okay, I remember that I read a paper by Schrodinger, and he said that I have to find the Hamiltonian. And so let's find the Hamiltonian. So you read that paper, and you say, okay, I have to, it's always, I start with classical physics. And of course, since you're an early physicist, you're really good at classical physics. Those old guys are better than we are. Those old physicists knew classical mechanics a lot better than we do, because we do quantum now. We have forgotten a lot of classical physics. Okay, but you're pretty good at classical physics, and so you say, all right, I know that the Hamiltonian is going to be equal to the kinetic energy of electron 1 plus the potential energy of electron 2 plus the kinetic energy of electron 2 plus the potential energy of electron 2 plus the potential energy which occurs because of the interaction between electron 1 and electron 2. All right, and that's purely classical. That's just the energy. And so now you say, all right, well, I know all these things. Now I got to write them in that weird way that Schrodinger told me to do. You know, I saw it in that paper. So let's write out this Hamiltonian. And you say, okay, so the kinetic energy of particle 1 is equal to negative h bar squared over 2m, where the m is the mass of the electron, times del 1. And I know the potential energy, oops, I made a little mistake there. And the potential energy of that guy is, can somebody tell me what the potential energy formula is for particle 1, electron 1? Potential energy of electron 1?
The Coulomb's force?
Exactly. So that's going to be minus something on top. What goes on top?
Two e squared.
Exactly. And on bottom we have 4 pi epsilon naught times what? What's missing on the bottom?
R1 squared.
Good.
Sorry.
Just
R1.
R1, right? R1, right? Because it's the energy. Good. Now we got to do, and so that I'm going to call that H1. That's that H1 is the Hamiltonian of just 1 electron in the hydrogen atom. I'll call that H1. And then I know that I got to write for the second one. H bar squared over 2m del squared acting on particle 2 minus 2e squared over 4 pi epsilon naught R2. Okay, that's the Hamiltonian for particle 2. Where these are the these are the isolated Hamiltonians. Meaning that's the Hamiltonian if I just had that particle on its own without the other particle. Okay, it's just a nomenclature I'm using. And then I got to add the potential energy of particle 1 and 2. Now, is the potential energy of particle 1 and bumping up against particle 2, is that potential energy positive or negative?
It's positive.
Exactly. Because it's both electrons have negative charge, so negative times negative is positive. Excellent. And so that's going to be E squared over 4 pi epsilon naught times what? What goes in the denominator? What?
R1
Or minus
R2.
R2.
Exactly. The distance between R1 minus R2. That's exactly right. Okay, and so I'll call this the electron-electron interaction, HEE, for the electron-electron interaction term. Okay, so this is my Hamiltonian, H1 plus H2 plus HEE, and they're operators, right? So now you got to solve this. So now to find the ground state energy, what you have to solve is this problem. You have to solve, so you must solve H and times a wave function. And that wave function is going to be a function of two variables. And this is what you got to do. You got to solve this. And if you solve this equation, then it will give you the ground state. The ground state is just going to be n equals 1. Okay, but you look at this Hamiltonian and you look at this and you just very quickly realize that this is way too hard. Okay, way too hard. And what makes it too hard is this thing, the EE. It's an interaction term that makes this problem just way too hard. It's too hard. Okay, so you're an experimentalist and you want to write a paper and you got to explain your theory. So what do? You look at this, you say, wow, that interaction term is just way too hard. I'm not smart enough to deal with that. So what do?
You approximate?
Yeah, and what's the first approximation that you try?
Set it to 0.
Yes, exactly. Very good. You're a budding experimentalist. That's right. You just say, man, that's too hard. I can't deal with it, so I'm just going to set it to 0. That's what we always do. So you just forget about it. It's like, I can't deal with it. Brush it under the rug. Forget about it. That's human nature. That's what we always do. We just set it equal to 0. We pretend it doesn't exist. Because now I have a Hamiltonian that I can solve. So this now is a Hamiltonian that we can solve. So this is actually an easy one to solve because these are independent Hamiltonians. Now I have the total Hamiltonian is the independent particle 1 plus the independent particle 2. Those are easy Hamiltonians to solve. So can somebody tell me what the solution is? Well, first tell me what the energy is. What are the eigenenergies of this Hamiltonian, E sub n? Well, here's the trick. You look at them separately. What is the solution of Hamiltonian 1 separate from Hamiltonian 2? What is it? It's just one electron circling a nucleus. It's the hydrogen problem. What is the energy? What is the energy of a hydrogen atom?
That's negative 13.6 over n squared.
Perfect. Except for one nuance. The nucleus has Z equals what?
2.
And so where does Z go for this formula? Does anybody remember how this formula depends on Z?
I think you multiply it, right?
By Z or something else?
Z squared, right?
Perfect, exactly. You multiply by Z squared, that's right. So that's what they both are. So that'll be of particle 1, and for particle 2, it's negative 13.6 Z squared over N2 squared for particle 2. And so that means that the total energy is just going to be the sum of them. It's just the sum of En1 plus En2 because the particles are independent. And so that means that it's going to be for the ground state. That means that for the ground state, I just take the smallest one, or I mean the biggest, most negative energy, and it's going to be Z squared times negative 13.6 EV plus negative 13.6 EV, right? And Z squared is what? What does that equal to? What's Z squared?
4.
Right. So you multiply this out and you get a number, and you notice that that number is negative 109. And you say, damn, that's too far from negative 79 EV. So you're looking at that and you're saying, that's not close enough. That's not good enough. Not good enough, because you know that to get into a really good journal, you need to do a little better than that. You know that the referees will tear you to shreds if they see that, you say, well, negative 109, it's close enough to my data, negative 79. The referees are going to say, no way, man, you're way off. That's like 50% off. That's not good enough. So you're thinking, shoot, what am I going to do? So you think, okay, well, it's not good enough. And so what is your next try? What do you do?
Variational principles.
Say it again?
What we just did before, the variational principles technique.
Exactly. Well, to be honest, what you really would do, what any normal physicist would do, is they would do perturbation theory next. So what you would do next is perturbation theory. And what you would do is you would calculate, the change in energy. You'd write some wave function down, psi, and then you would stick in the perturbation, which is the electron-electron interaction, and you would calculate that. That I'm just saying that's what you really would do. But suppose you do this, and suppose you did that, and it turns out that the number's not so good. You get a number that's not good enough. So it turns out that you can do better with the variational principle. Let's just suppose that it was not good enough.
Professor?
Yeah.
So in terms of determining whether a situation is better addressed by perturbation theory or the variational principle, is that just to bash it out and do both things and see what kind of works?
Yeah.
Okay.
Yeah.
Okay.
It is. That's right. There's no good general principle. It's just a case-by-case basis.
I see. Okay, thank you.
Okay. And so, but suppose you were to do this by perturbation theory, then let me ask you a question. What would be the psi that you would use? Which wave function would you use?
Would it be the product of the two individual ones?
Exactly. Perfect. Psi of R1 times psi of R2. That's right. Now these are hydrogen wave functions. It's the ground state of hydrogen. So what is this function psi? What is this function? And this is what I'm thinking of, psi, and remember NLM is the eigenstates of hydrogen. So what NLM is it?
Isn't it 100?
Yes. That's right. And to put them in, you would and to now you have to symmetrize the wave function because there's two electrons. And so that would be your ground state, but that's a symmetric function upon particle exchange. So you would have to multiply it by a anti-symmetric spin function, right? The singlet state. But for this problem, we're not including any spin terms. We're not including spin orbit coupling or anything that depends on spin. So we'll just sort of forget this. The spin part is not important for this problem, but I just want to mention to you, it is there. But it just kind of gets carried through, and it doesn't really matter. So let's just sort of drop out the spin part, and I'll just say spin not important here. And so let's remind ourselves what this function is, psi of R1, R2, and let's plug in these functions. And when you plug in those functions, you're going to find that what you get, this product, is equal to this. E to the negative Z R1 plus R2 over A naught. Okay, so that is actually the wave function when you plug in these functions for psi 1, 0, 0. Okay, so it's just something you look up in a book. It's not hard. Where A naught is equal to the Bohr radius. I didn't write down the formula for it, but it's equal to the Bohr radius. Equals 1/2 angstrom. Okay, so that is, and that's easy to find. You just look it up in a book. Okay, so that would be the unperturbed states. Now, okay, so suppose that we did perturbation theory with this function, and suppose it wasn't good enough. Then what we would do is we would say, okay, let's try the variational principle. Now let's try the variational principle. And to do the variational principle, what we're going to do is we're going to have to pick a psi, which is a function of, it's going to have to be a function of, you know, particle number 1, particle number 2, but there's also got to be some parameter that we vary, parameter. And then what we're going to do is we're going to calculate the expectation value of the Hamiltonian for that state, and that's going to be the integral of psi star h psi d cubed r divided by the normalization factor, psi star psi d cubed r. And then we're going to minimize with respect to lambda. And we'll plug, and then we'll plug the thing we get back in. Okay, that's what we're about to do. But before we go further, I have to ask, what is the psi? What psi are we going to pick? We got to ask this question. This is the big question. What is psi? What is lambda? This is the big question. And this time it's not quite as easy as last time, but I'm asking you, what is it? What is it? What is the psi? Which psi do we pick? Can you guess? What? And this is always tricky, you know, like what wave function do you pick to do the variational principle? You have to use intuition. Like what, can anyone guess, like what kind of wave function should you pick? And what should lambda be? And I'll give you a hint. It's staring you in the face. And it's not my face.
How about the ground state that you have boxed up there?
Perfect. That's exactly right. Okay. Because what you're saying is, you know, and the reasoning would be, this is how it works. You're like, I don't have a clue. I don't have an effing clue what to do. All I know is the simple non-interacting wave function. That's the only thing I know, because, you know, I can't solve anything else. I don't know. So if that's the only thing I know, why don't I just use that? Okay, I'm serious. That's how it works. All right, you just go, geez, I don't know nothing. Let's just go and do the only goddamn thing I know, and that is the non-interacting ground state wave function. That's all you know. So use it. Good. But now stare at it and you say, okay, there it is. But what is going to be my parameter that I vary? So you got psi, very good. But what is the parameter?
Is it A naught?
So what you're saying is A naught is like a Bohr radius, but you're saying let's turn it into
A
a
radius.
variable. Is that what you're saying?
Yeah, turn it into just a regular radius.
Perfect. Good. That would work. Very good. That's exactly the kind of thing that you do. Good. That's right. That would work. That would give you the right answer. It would work. But there's another way to go. That's one choice, but there's another choice. And I actually want to do the other choice. So what's the other choice?
I mean, Z by process of elimination.
Exactly. Now, what you said A naught would work. Okay, I want to give you credit for that. You know, that's exactly perfect. That would work. But it turns out that Z is physically a little nicer. You know, Z is a little nicer. So let's choose Z instead of A naught. But A naught would have worked. So let's choose Z. And there's really a physical reason for choosing Z. So Z is now our parameter, okay? Z, remember, for helium, Z has a real number. What is Z? Tell me.
2.
It's 2, right. But now we're going to turn it not 2. It's now, for us, it's no longer 2. It's a variable. All right, Z is now a variable. And we're going to calculate all these expectation values for Z, and then we're going to like minimize with respect to Z, and we're going to find what Z is. But so Z is now a variable. And I want you to see that this is actually quite physical, because the nucleus has +2, Z equals 2. But now what happens is, this is the way to think about it. I got 2 electrons. I got 1 electron here, and then I got another electron also out there. And I just want you to see that that first electron sees Z equals 2. But that second electron, what does he see when he looks inside to the nucleus? Does he see a positive charge of 2? Yes or no? Just use simple electrostatics. What does he see? He sees a charge of what? The second electron looks inside to the nucleus. What does he see?
Just 1.
Right, because because the other electron has canceled some of the charge. So he sees a smaller Z. So what the word we use is, we say this guy provides screening. So this is called screening. So the point is, so the Z effective is less than 2, because one electron screens each electron screens the other electron. They're screening each other. And so each electron, when he looks at the nucleus, he sees a smaller charge. So this idea that the effective Z is smaller than 2 is intuitive. It makes sense from a physical perspective. And so that's why we choose Z, because there's a physical reason to make that into a variable, because you know that for the correct problem, Z, the effective Z is going to be a little smaller. So that means there's a physical reason to choose Z as your variational parameter. I just want you to sort of see that. It's not just arbitrary. It's not just a bunch of arbitrary gobbledygook. There's meaning to there's meaning to it. Okay, so now let's calculate our stuff. Okay, so now it's time.
Professor?
Yeah.
So Z effective is not just simply 1, but it's...
Yeah, the reason it's not just 1 is because, remember, the electrons are distributed. They're wave functions. And so, you know, they're all distributed over all space. And so, you know, it's not so simple that just 1 is in is in front of the other one. You know, they're both distributed throughout all space. So, okay, so it's just a little bit more complicated. Does that make sense?
Yeah, okay.
Yeah, all right. So now let's calculate it. So now it's time for us to actually solve the problem. And so what we're going to do is we have to now calculate these horrific integrals. So now calculate these terrible integrals, calculate. But the nice thing is that the one nice thing is that this wave function is normalized. So at least we don't need to do that normalization thing, okay? It's normalized already. That's from last semester, okay? So that's your wave function, it's normalized. So now we have to calculate this Hamiltonian where the parameter now is z, and we got to calculate the, so we know that the Hamiltonian is the Hamiltonian for particle 1, for particle 2, and the interaction term, which I wrote above. Sorry for not writing it again, but too much writing. So now we got to calculate the expectation value for these three parts. For that wave function, and then of course we're going to do, you know, the derivative with respect to z of this, and set it to 0, and then we're going to find the minimum, you know, the minimum parameter, z min. Okay, that's what we got to do. But now let's notice something. Let's notice that our wave function psi of r1, r2 is this function. It's equal to z cubed over pi a naught cubed e to the negative z r1 plus r2. There's a mathematical trick to notice, which you wouldn't have figured it out on your own probably, but once someone points it out to you, you can see it's kind of cute. We notice that this is no longer an eigenstate of H1 and H2. It almost is, but it's not. And the reason is because if z was 2, then it would be an eigenstate, but z is not 2. Z is an arbitrary function. So let's do a very clever thing. Let's define this. H1 prime is equal to P1 squared over 2m minus z e squared over 4 pi epsilon naught r1. Now, this psi is an eigenstate of H1 prime. It's an eigenstate of that, where z is a variable. And so now here's the cute thing. Let's notice that H1 is equal to H1 prime plus z minus 2 e squared over 4 pi epsilon naught r1. And this is just a mathematical trick. We notice that this is the thing we want, and this is the operator, and we know that our function is an eigenstate of this operator, and this is the difference between them. And so what that means then is that the expectation value of H1 is equal to the expectation value of H1 prime plus the expectation value of z minus 2 e squared over 4 pi epsilon naught r1. And the expectation value of that is just the hydrogen atom energy, which we know is z squared times negative 13.6 eV. And that is the trick. And so then we see then that H1 is equal to z squared times negative 13.6 eV times the plus the expectation value of z minus 2. Actually, let me write that easier, because you can sort of see that it's actually something quite easy. Z minus 2 e squared over 4 pi epsilon naught, just a constant, times the expectation value of 1 over r1 for the wave function z. And this is actually an easy thing to calculate, easy. But I don't have time to do that. It's using the Virial theorem. And so then you can see, so then when you go through the algebra of the Virial theorem, then what you'll find is that this thing is equal to it's equal to z minus 2 e squared over 4 pi epsilon naught times z over a naught. Okay, because that's what this thing is equal to, z over a naught. So so then what we see then is that then what we have to do is, so then we can see that this is also equal to the expectation of H2 by symmetry, and it's equal to this. Okay, so that part is actually pretty easy. But then you have this hard integral to do. Then you have to calculate this interaction term, HEE, which is actually a lot harder. And so when you set that up, it's going to be this integral, and it's going to be, it's a hard integral, but it's a doable integral. You can have that function psi star of R1, R2, and you're going to have e squared over 4 pi epsilon naught R. Oh, shit. I don't know why this did this. It went crazy on me. Okay, so then it's going to be R1 minus R2, the magnitude times, okay, and so times the other function, psi of R1, R2. Okay, so you got to do this integral. So this is a hard integral, but not too hard. It's a famous integral. It's in the book. And you can do it. It's not too hard. And what you'll find then is that this integral is equal to 5z over 8 a naught times e squared over 4 pi epsilon naught, which is equal to 5z over 4 times 13.6 eV. Because you'll notice that that's just sort of the hydrogen ground state energy buried in that formula. Okay, so that's what you find when you do that integral. And so when you put it all together, you see then that you're going to get the expectation value of the Hamiltonian for that wave function is going to be negative 2z squared plus 27 over 4 z times 13.6 eV. And so then you can minimize this with respect to z, d dz of this, set it equal to 0, and what you're going to find is that z is equal to 27 over 16. And I just want you to notice it's smaller than 2. And that means that the screening has made the effective z smaller than 2. So what is it? It's 27 over 16. We just calculated it. And so let's plug it in, then plug that back in. And what you get is that you get the expectation value of h for the minimum value of z, the z that gives you the minimum, that minimizes it, and you get this number, minus 77.5 electron volts. And notice that that's only 2% off. It's only 2% higher, and it is higher than the true energy that we measured experimentally, which is negative 79 eV. Okay, and that's it. So I know I went over, I'm sorry, but that's the answer. And we just solved a seriously hard problem using the variational principle. Okay, folks, that's it. Bye-bye.